Right, well, good morning, everybody. As you see, it's fallen to me to get things started. So perhaps the first thing I should do is to thank Adrian and George, the organisers, for bringing us together so that we can begin to highlight and discuss some of the important issues that come under this umbrella of mathematical aspects of geophysical fluids. And you see where we're starting. We're going to start with the atmosphere. As always, some of you will have heard this before, the background to getting started in these sort of problems is it's all down to Adrian. I was very reluctant to work at problems to do with the ocean, but he persuaded me otherwise, and I think that's been reasonably successful. And then, towards the end of last summer, shortly before I was due to come and visit here, Adrian contacted me and said that he really thought we ought to have a look at the atmosphere. I am not going to tell you the full story. It would take the rest of the hour. It's a long and tedious story. I will cut it very short. I said no. He said yes. Then he said yes again. I resisted. But as you see, I gave in. I tried to explain that, in my view, doing some really careful fluid mechanics for the atmosphere with the hope of getting a reasonable representation of what was going on, I thought was likely to be beyond what I would call classical fluid mechanics. That's taking the full set of governing equations, non-dimensionalize, scale, do whatever, and do proper asymptotic expansions. Eventually, I think, I found a way forward, and that's what I want to show you today. I tried to develop a systematic representation of the atmosphere. Once I'd got those equations, we, as Adrian and I, then started to look at what we could learn from these equations, some of which is classical, some of which is a little bit new, and I think there are opportunities for taking this very, very much further. So, I won't read all the way through that, but that'll give you an overview of what we're going to try and do. So, I'll describe the background in very simple general terms, set up the governing equations and the non-dimensionalization that is associated with them, the structure of the asymptotic solution, what the equations look like when you've carried out the asymptotic expansion, and as you see towards the bottom here, we'll have a look at some examples. Before I forget, again, some of you would have heard me say this before, please do not hesitate to ask questions during the talk. If I can give you a quick, simple answer, that's probably more efficient than trying to remember it all to the very end and then me maybe having to go back through the screen. So at any stage, do please ask. Right, so I guess that we're all pretty familiar with the general makeup of our atmosphere. And this, I believe, it really is quite an amazing photograph. What you've got here, this is the Earth. As you see, it was taken by NASA in 2010. The orange-red is the troposphere. Just above that, the pink is the stratosphere. The light blue is the mesosphere. And you can just see very much darker, and then going into black, is the thermosphere. I never imagined, I have to tell you, you could actually take a photograph and see the layers in the atmosphere. The sun, by the way, as you might imagine, is just below the horizon, shining up into the atmosphere. And obviously, it's the different structure that makes up each of those layers that causes the color change from the sun. So we're going to be talking about loosely all the atmosphere, but predominantly I'll be talking about the troposphere. Another picture that you'll be very familiar with, the temperature profile throughout the atmosphere, and again, we're going to be mainly dealing with the troposphere. That does contain about 75% of the mass of the atmosphere, and of course it's where most of our weather occurs. And it's bounded then by the tropopause. And as I said a few seconds ago, the main interest is going to be with the troposphere. It's that particular region that we're going to be interested in. Okay. If one looks at the literature, one finds that, from my point of view, it seems a rather haphazard approach. So quite typically, one would analyze a very, very specific problem and try and construct a model for that particular problem, a particular phenomenon within the atmosphere. So specific and special models chosen to suit a particular calculation. There may be geometric simplifications, the F-plane or beta-plane. There may be some measure of compressibility via the Boussinesq approximation, which is then used in the gravity term only. And from my point of view, and this is the fundamental problem, I believe, there is no systematic approximation procedure. You don't start off with a full set of equations, introduce a parameter, hopefully just one parameter, and construct an asymptotic solution, which furthermore one hopes, but one needs to check, is uniformly valid. So what I'm going to do is to use an appropriate, complete set of governing equations. I'll outline them in a moment. And I'm going to make one simplifying assumption only, namely the thin shell assumption, nothing else. And then, as I've said there, just see where that leads us. Okay? Right, so I'm not going to write them out because I couldn't even get some of them single equations on a single screen, and you could read it if one takes full set of Navier-Stokes in spherical coordinates, in a rotating frame, compressible, and for variable viscosity. I will, of course, give you slightly reduced versions when I've shown you where we're going. Right, so here we are. We do have Navier-Stokes for a compressible fluid. I'm going to take a variable eddy viscosity, which is varying in the vertical direction. It's one of the modeling, overarching modeling simplifications that I'm going to impose. The scaling arguments indicate that variations in other directions are much weaker than that in the vertical direction. We need an equation of mass conservation for a single component gas. Now, this was one of the areas where I really did agonize because, of course, we have, for example, water vapor. Water vapor makes up about 3% by mass of the atmosphere. So in terms of the contribution it makes in volume, space, it's very small. However, it is very significant when we start asking about heat sources. Water vapor being converted into water droplets is a significant source of heat energy. But I'm going to overcome that, I hope I can convince you, by allowing, albeit a single component gas, a general heat source, but no specification as to what the nature of the heat source will be. We need an equation of state, the classical equation of state for an ideal gas, and of course, we need a suitable version of the first law of thermodynamics. So this is our starting point. What I'm going to try and do is to start with this set of equations, carry out a systematic restatement of them, introduce parameters, non-dimensionalization and parameters, and as I indicated on a screen a couple of screens ago, see where that leads us. Yes, sure.
Okay, so before you get started, the eddy viscosity problem is a kind of difficult one in our field, as you know, and do you plan to have it dependent on resolution? I mean, models, for instance, nowadays are entering what's called the gray zone, where they don't really know what to do with conversations, which eddy viscosity is one of. So what do you think of eddy viscosity? I mean, ultimately, if you had a model that could compute to arbitrarily small scales, you shouldn't need it.
Right. The eddy viscosity will be arbitrarily assigned as a function of vertical coordinate. I'm not going to specify it any further than that. It can be a function of the background temperature, if you wish it to be, but I can't take it any further than that at the moment.
You're not associated with a numerical discretization.
No, I am absolutely not.
You're saying as if there is a given eddy viscosity in the atmosphere.
Yes, but when you see the equations that I'm going to develop, I would anticipate that I'm hoping that they will be very useful for numerical analysis, and that at that point you can put in almost anything you like for the eddy viscosity. Okay, but for in terms of analysis, I need to be a little bit more specific. Right, thank you. Okay, so of course I need to introduce spherical coordinates, so this is very much the familiar picture. By the way, for those who worry, the prime, and I've got them down here, denote physical dimensional variables. Once I non-dimensionalized, all the primes will disappear. So we've got phi is the azimuthal angle, theta is the polar angle. Of course, we're in a rotating frame, so we've got a rate of rotation appropriate for the Earth. Okay, I'm going to talk here about steady flow. We're busy working on the corresponding unsteady problem, and it does look as though much of the structure that I'm going to show you goes through even when the flow is unsteady. But for here, I'm going to stick strictly to steady flow. Okay, of course, we've got other variables to worry about. We've got the pressure, and I'm going to invoke Stokes' hypothesis, i.e. dynamic and thermodynamic pressures are the same. As I've already commented, we'll have a single component of gas, and that's its density. We'll have a temperature, of course. We have the eddy viscosity and acceleration of gravity at the surface. So, non-dimensionalization. There are two levels of this non-dimensionalization that I want to show you. The fundamental one, rather the obvious one might say, is to introduce a measure of the thickness of the atmosphere. We might limit that to the troposphere if we wish. So I've non-dimensionalized distance and I non-dimensionalized the velocity scales. As you will see shortly, this is the appropriate one to use. I'm taking d prime to be a suitable depth, which for the work I'm going to show you here, I take to be the maximum thickness of the troposphere. And r prime is the average radius of the Earth, of course. Right, obviously we've got to non-dimensionalize the other variables. When you see an over bar here, these are just average or typical values of the appropriate quantity. So for example, density and viscosity. Script r is the gas constant. Now, when you're doing a thin shell approximation, so you're going to, well, you've seen it already, you've got the epsilon appearing up there. You need to worry very much about the scale associated with W. And I've put that in here by using the measure K to indicate what the scale of W will be. In a consistent thin shell approximation, that has got to be order epsilon. I've just chosen it to be K is equal to epsilon in this choice. That will give rise to a thin shell approximation. What you'll observe, therefore, of course, is that the velocity component in the vertical direction is an order of magnitude measured by epsilon, smaller than u and v. Yet, when you construct the equations, u, v, and w come through at the same order. That is typical of a consistent thin shell approximation. Okay, so now I'll start writing some equations out for you. I avoided writing out the full Navier-Stokes. What I've done here is to apply the thin shell approximation in part. So I've applied them to the viscous term. I'll give you the definition of the parameters in just a moment. Down here. So those are the three components of our Navier-Stokes equation, which I will write out individually in a moment or two. The d by dt is the normal operator, except, of course, although it's the material derivative operator, because of the choice we've already made, there's no partial d by dt in here, so I've suppressed it. Right, I think that's straightforward enough. Now, of course, we're going to have an equation of mass conservation using the definitions that I've already put on the board. We need an equation of state, and this is my choice for the thermodynamic equation, the first law. Q is the non-dimensional general heat source terms. Well, I'm not going to specify what they are. Now, one of the classical problems associated with doing these sort of calculations is to try and find some appropriate model representation for Q, start with that, and then use that as the feeder to then hopefully solve the problem. In some sense, loosely speaking, get the temperature, the pressure, then get the density, then the velocity field. What I'm going to show you, excuse me, one of the things I've noticed, sadly, as I get older, I think I can keep going, except I dry up rather more usually. Happens a little more often nowadays. So, as you will see, I'm going to think about this problem in a rather different way, but that would be the classical thinking. Okay, here are the parameters where we've got a Reynolds number. I've introduced the parameter G, rather an intriguing parameter, which turns out to be really quite important in terms of the fundamental description of the background state. You can interpret this as being the ratio of the square of two speeds, the speed of gravity waves in a fluid of depth d primed, and the speed at the surface of the Earth at the equator due to the rotation of the Earth. And you see that turns out to be a moderately valued parameter. And we've got specific heat and the thermal constant here. Okay, I'm now going to systematically carry out the thin shell approximation, which I've done a little bit in part, as you've seen, for the system of equations that I've now shown you, suitably non-dimensionalized and with all the other parameters that I've just described to you held fixed. The only expansion parameter I'm going to use is epsilon. Everything else will just be a fixed order 1 number. Okay, so here are our 3 equations, component equations that make up Navier-Stokes, and I've given you the error terms in each case. There's the equation of mass conservation, the equation of state, unchanged, and the corresponding form of the first law. So that's what the system now looks like with the appropriate error terms incorporated. Of course, because of the nature of the parameter dependence, it will be natural to look for a very simple structure to the asymptotic solution of this system. So, structure of the asymptotic solution. I'm going to seek a solution which is generated in powers of epsilon for every term, every unknown function in the system. Keeping all the other, as I said a few seconds ago, keeping all the other parameters fixed. They can take any values whatsoever, but they do not vary in epsilon. They're not functions of epsilon. Okay. One of the issues that one has to address when doing a calculation like this is whether such an expansion could we prove it? Very unlikely, sadly. I can't give you a theorem here, but what I can tell you is that the solution that I'm going to construct has no evident singularities whatsoever in the velocity, the pressure, or the temperature fields. Furthermore, and this is usually where you would have a problem in the thin shell approximation, Z, you've got terms like epsilon times Z. So if Z goes to infinity, you're going to be in trouble. But if you're talking strictly about the atmosphere, and the equations I've written down are valid only for the atmosphere, then if you, for example, limit yourself to the troposphere, then Z will sit on 0,1. If you do take the same non-dimensionalization, that is the d prime that I introduced, and you wish to go to the edge of the atmosphere where these equations pretty well hold, getting a bit iffy when you get to the very top, then Z perhaps sits on 0.8, something like that. Without any doubt, it is strictly, Z remains strictly bounded for the application of the validity of the equations that I wish to use to apply to the atmosphere. So we can therefore anticipate, expect, hope, if you wish, that we have a uniformly valid asymptotic solution. It means that the higher order terms, I'm going to construct, as you'll see in just a moment, order 1 and order epsilon. Those are the 2 we crucially need. They naturally fall out of here, and they have a natural interpretation as well. That the higher order terms, epsilon squared, etc., remain strictly that size. They remain strictly smaller order in the sense of epsilon tending to 0. Okay, so apply the expansion procedure to the equations that I showed you a few moments ago. You automatically generate then a background state, which is the order 1, and then we get the perturbation of that background state. So already, in a sense, I suspect we're moving into an arena which is not always covered in atmospherics. I'm going to have a general background state, satisfying the equations, which then I'm going to perturb. It's really what the background state looks like. That's going to be rather trivial, of course. And then what happens at the perturbation state? Okay, so at the leading order, we get, perhaps for some of you, a very familiar picture. This is going to describe the background state of the atmosphere. It has a solution, which depends upon GZ, but notice because of the scalings and background geometry, we also have a minus a half cos squared theta sitting in there as part of the argument of the function. I guess, yes, okay. We then get the first law, that's here. It comes down to this, and of course, again, very familiar, there is a solution valid for the troposphere in which Cp dt naught by d zeta, as I'm calling it, this quantity, plus 1 is 0. That's an exact solution of that equation because T naught is linear in zeta. That term is 0, and there's no external heating source. So we don't need, to maintain this, we don't need external radiation, and we don't need internal heat within the atmosphere itself. That won't apply, of course, otherwise. So so I think I've got a little bit more about it, yes. The background state for the temperature, I've written it out in a little bit more detail. I've imposed a boundary condition here. I've said, let's suppose that we know what the temperature is at the bottom, z is equal to naught, and along theta is theta naught, and I can take that to be the line of latitude nearest the sun, accounting for the fact that our Earth is tilted. It needn't be sitting over the equator, for example. That needn't be the hottest point. Of course, we can then work out the pressure and the density. What's important is that once you've specified that the troposphere is sitting in physical terms between naught and d primed at the, or in the neighborhood of the equator, then the solution that we're writing down can only be defined in a specific region. As you see, I've now specified absolutely clearly, so now I know what I'm using d primed as here. I'm making sure that the top of the troposphere is at z is equal to 1 at theta is equal to theta naught. What this immediately means, by virtue of that dependence, is that the top of the troposphere necessarily drops as you approach the pole. So, for example, if you take the maximum height of the troposphere to be round about 16 kilometers, then it will drop to between 5 and 6.5 kilometers as you approach the poles. Now, I haven't actually, that I think is well known, but I haven't seen that described in the simple geometrical terms here, which is solely because of the geometry. This is the cos theta effect coming via the geometry and rotation. Okay, so that's just the background state. It's there, we're not going to be that interested in it, but we need to know it's in place. Okay, at order epsilon, this is where things get, I hope I can convince you, rather interesting. Okay, so at order epsilon, this is the system. These are the three equations that constitute the three components of Navier-Stokes, and I'm sure some of you will recognize some of the terms in there. I thought I'd put it on here. I'm going to use it in a moment. Observe, I'm going to rewrite the perturbation in the density by defining it in terms of the derivative of a function. So rho 1 is going to be dr1 by dz. I'll come back to that in just a moment. Okay, the equation of mass conservation becomes that. Observe, I should have said it earlier, but it's more obvious here, isn't it? You'll observe that what we've got here is u, v, and w all appearing at the same order. We've got v and w down here appearing at the same order. You do not lose w in a thin shell approximation. It's a very special problem to set w is equal to 0, and it's not physically consistent with the equations that we've got here. So we've got equation of state, and we've got the first law in this system. The question now is, what can we learn without any further approximations? What can we learn about this system? You'll observe that we've got all our parameters in here. We've got the Reynolds number, we've got G hidden inside, and therefore geometry hidden inside zeta. We've got all the terms you might hope and expect to see sitting in the first law of thermodynamics. We have a general heat source term sitting in there. We've said nothing about them whatsoever. Everybody still okay? All right? Okay. Right, so it's obvious that we should work not in terms of phi, theta, and z, but rather because of the underlying dependence in the background state, phi, theta, and zeta. So just carry out a small adjustment, and let's see what we get. Well, I'm going to use the R1 that I introduced you to a moment or two ago. I can then integrate to find out what the perturbation pressure is, the P1. Okay? If I use that, which of course has got R1 in it, in the equation of state, I get this equation for R1. It's at this point I'm going to make what turns out to be a crucial maneuver. Let me introduce the perturbation temperature, T1, write it in this form. Let me write it as T0 squared, which is the background state, times by the zeta derivative of Tor1. Sorry, some of you might say tau, but the Greek I was taught to call it Tor1. So that Tor1 is now playing the role of the perturbation temperature. And to be quite precise, I'm going to define Tor1 in that form. The arbitrary function appears down here in a moment. So with that choice, I can now completely integrate and write in this very simple form the expression for R1, which amounts to knowing what the density perturbation R1 is. Okay, we haven't quite finished yet, though. Oh, the arbitrary function G that I've just mentioned is fixed by the background state and the perturbation. So it's a function of zeta and what's happening on the ground level. Okay, it's convenient now to write dr1 by d zeta as the sum of two parts. A part that involves the Tor1 and something else. I've just called it R1. When you do that, the first law takes this very simple form. Okay? L0 is the operator that we had before, but now expressed in terms of phi, theta, and zeta, and we can determine what R1 is. R1, you'll notice, depends only on the background state and this arbitrary function G. Okay? We still haven't quite finished. Okay, so putting all that in the first two components of the velocity field Navier-Stokes, then we get this and this. But we can make that look a lot neater. Let me introduce a function, sigma 1, defined in this fashion. When you do that, you get, as your governing equations at order epsilon, which has got the linear dynamics and the thermodynamics in it, we have a structure here, which again I suspect for some of you will be rather familiar, but with a much more general type of forcing function. Knowing sigma 1, we can solve the horizontal velocity field. How would we get sigma 1? Well, if you know the background state, we do. Notice it's got the geometry in there as well. And we know what the perturbation temperature field is, because that will give us Tor1 from T1, and the temperature field is reasonably well known. We can compute sigma 1. Sigma 1 will then drive the horizontal field. But furthermore, if you know what sigma 1 is, let's suppose we do it that way around. Choose a sigma 1 to force this to give solutions we're interested in. If you've chosen sigma 1, then you know Tor1. If you know Tor1, then you know T1. Therefore, you know everything on the left-hand side of the first law of thermodynamics. You therefore know what the heat sources have got to be to maintain that motion. I'm turning the problem, I'm suggesting, on its head. Instead of given Q, solve the problem, set up a solution of a problem that you're interested in, and then determine what the heat sources have got to be for that. And those heat sources are made up of two parts, some of which are moving around, so it'll be like latent heat being generated at points that are moving with the fluid, and background radiation. It'll be anything you want it to be. It's whatever it turns out is what is calculated, what is computed, when you work out the left-hand side of the first law of thermodynamics. So, where have we got to? So we use these two to get the horizontal velocity field. We've got the equation of mass conservation. That gives us W. And as I've just said, we use the first law to generate the heat sources that are consistent with that solution. I'm going to pause. Any comments?
Yep.
Sorry, you mean the big G up there? Yes, it's what it was on the previous graph. Here we are. It came in, if I go back one more, it came in here. Okay, it's essentially the integration of this. It's the arbitrary function.
Have you specified, do you need to know what that arbitrary function is?
Oh, right, okay, yes, you do. And if you, let me get down, it is up there. So it's in, and it's here as well. So it is part of sigma 1. It's part of the forcing. Yes, okay? Well, it depends on how you think about it. You see, if you're asking the question, let me go one stage further. If you're asking the question, let's solve this system given a sigma 1, and from that you then determine Tor 1. To determine Tor 1, you've got to know big G, but we can interpret it. We know what it is, but you do have to have it in the system. Yes. Okay? Yes, sure.
I've seen something previously which looks like geostrophic balance, but I'm looking for that thermal wind balance. Where does that
I can't. Well, can I go through my examples, then you can get back to me? Okay, yes. Right. So, I better just deal with this too. You can do the whole process in the higher regions of the atmosphere. Everything I've just shown you essentially goes through. So, we start with background state, but now we make different choices. So, obviously, if we're in a proper pause, in a pause, then we're going to set T naught as a constant. Previously, we had Q naught is 0. Q naught now will no longer be 0. You need some sort of heat input to generate that solution. For the other regions, the stratosphere, mesosphere, and thermosphere, again, you just make a suitable choice for the temperature variation. Again, suitable heat sources will be required. Essentially, the system I've just shown you goes through, but with relatively minor changes to the definition of the functions P1, little r1, and big R1. So you can describe each level, each layer of the atmosphere, not just the troposphere, which is what I'm going to talk about in detail in a moment or two, but the tropopause and the other pauses and the 3 layers above. They follow the same pattern. The difference being how you solve this problem to describe the underlying background structure to the atmosphere. Okay? Right. So, let's deal with some very particular results. So, Ekman's spiral, that's almost trivial here. All we need to do is to make a choice that sigma 1, this driving function that I've introduced, is only a function of zeta. Don't need to say any more than that. That is sufficient to generate the familiar pair of equations, except, of course, that this is a variable eddy viscosity. In here, the m is essentially a function of zeta. We've got a compressible gas, of course, and it's written in spherical coordinates. So we've got arguably the most general, reasonable form you could ever expect to have to describe the Ekman spiral. If you make a very particular choice of sigma 1, I've just said any function of zeta will do the job, then you can go through the argument that I've just outlined. That is, what you can then do is to generate the perturbation temperature field, and with that, you can then determine what particular heat sources would drive that particular solution with that particular choice of sigma 1, all of which are going to be Ekman spirals. Right. So we look at geostrophic balance. This, I'm going to have to write it, for some of you, in a more familiar form. It isn't the comfortable form in terms of the structure I've been showing you, but it's the natural thing to do to compare. So I'm going to introduce the perturbation pressure, in which case we get the system that's going from sigma 1 to P1, which at first sight you might think is very good, but of course you see we've got an extra term coming from the geometry appearing in here, but we can remove that. So, so I've commented here that the pressure field is not as well documented, understood, don't have data for it, as, for example, the temperature field is much more reliable if you're going to use this sort of approach, to use the temperature field rather than the pressure field. But nevertheless, if you stick with the pressure, if we just redefine it by taking out, equivalently, this little bit here, we will then get the equations, in the absence of viscosity anyway, which take exactly the classical form for the geostrophic balance. In other words, I would argue, because I've done this, I would like to think carefully, systematically, we do have a proper approximation, although you have to be a little bit careful about the pressure that you use. So it has to be what I've called a capital pi 1 in here. It isn't the original pressure because you must take out this part before you start. Okay, so let's do something a little more exacting. Let's see if we can have a look at the Hadley-Ferrell polar cell structure, which describes the cells from the equator to the pole, 3 of them. Could we recover that? Can we say anything about that particular flow configuration? In order to give you some very, I think AD is going to disagree, fairly simple explicit results, I'm going to make 2 simplifications here. Not essential, it just means that it's massively complicated, and I think it's on the edge of being possible to do analytically. It certainly makes it a trivial numerical problem if you want to get rid of these 2 restrictions. So, for the purposes of this demonstration, I'm going to just take the viscosity to be constant. We don't believe that the variation of viscosity is inherent in what you're about to see, but we could put it back in if we needed to. And most of the data is represented in terms of zonal averages, and that certainly simplifies things a little, so I'm going to perform the zonal average as well. Okay. Furthermore, we can write the 2 equations for the horizontal motion in a compact complex form by introducing u plus IV, u0 plus IV0, and the resulting equation for the complex valued function z0 is this equation. The over bar is that zonal average that I've just mentioned. Okay, so what's nice about this solution, I think, is that there is an exact, and it corresponds to an inviscid, solution of that equation. That is, if Z0 is linear in T0, then sigma 1 has got to take this form. The theta dependence in here can be anything you want it to be. Theta dependence is not prescribed. So providing these 2 conditions are satisfied, the relationship between alpha bar, A bar, beta bar, B bar is all that's required to ensure that this object is an exact solution of that equation. But it is the inviscid solution, as you can see. This term doesn't play a role at all. So how would we go about constructing a useful, relevant solution using that piece of information? I hope I can justify that this choice is a perfectly reasonable one to take in a moment or 2. If you can't find an exact solution, you're going to have to work a bit harder. Okay, oh yes, notice that this exact solution only relates to the real part. These functions are real, so it only relates to the real part of Z0, not to the imaginary part. So it doesn't relate to V, it only relates to U. Okay, so obvious thing to do now, write the solution of the sum of 2 parts, this particular integral and a complementary function. That has to satisfy the equation as specified. Remember, we've still got compressibility here, so I've got to take out that rho naught power, so I've dealt with that. If you take out rho naught, you can transform the equation into a complex valued Bessel equation. Right, there are the various definitions. It does take 2 different forms depending upon whether you're in theta positive or theta negative by virtue of this plus or minus I. Lambda is related crucially to the Reynolds number, square root of the Reynolds number, as you would be expected, I think. Okay, the solution of this equation is just made up of Bessel functions of the first kind, complex value though, remember. And nu is rather nice. It is just 1 over 1 plus Cp, the coefficient. Right, so complete general solution, therefore, is made up of the complementary function, the Bessel functions, and the particular integral. We now need to specify the boundary conditions. So, the boundary conditions are that at the very top, we're in the troposphere, at the top, which is in terms of zeta, this object here, it's got to be what I've specified coming from the particular integral, and a little bit I don't yet know. I don't know what's happening to the V, the meridional component, at the top. But that's all I need to know about the meridional component. Of course, at the bottom, I'm going to impose the conventional viscous, classical viscous boundary condition, a no-slip boundary condition at the bottom. So I impose this at the bottom. So the only thing we now have to do is to find the theta dependence, which I've told you, we haven't specified that at all. The theta dependence in that solution, and that can be anything you want it to be, anything appropriate, anything that mimics the data is what we're looking for here. Okay, I've also, just to show you the flexibility in the calculation, I haven't chosen theta naught is 0, I've actually chosen it to be minus 10 degrees, just to show you what happens when you're not quite aligned exactly over the equator. Okay, I now need to make choices for the functions. I'm going to be guided by typically this sort of data. So what we've got here is the mean zonal wind speed from the top of the troposphere, that's this line here, down to near the bottom, which is this line here. And what I have done is to assume that the variation from top to bottom is linear in zeta. That's that T0 dependence that gives me my simple, exact solution of the problem. The data for the top of the troposphere in terms of the meridional speed is not so well known, but we can have a stab at what that ought to look like. But you can choose anything you want to and plug it in and see. Remember these functions here, these functions of theta, you just choose them and plug them into the solution that I've already expressed, already written out explicitly. But that, just to schematically, is what I chose as the relatively simple functions that mimic what we've got over here. So the red curve is the zonal velocity field in red, sorry, at the top. The bottom of the zonal is the green, which is based roughly on what I'm seeing here. And I've had to choose an appropriate meridional top, which is the one in blue there. Now, what we would like to be able to do, and in principle, this is the approach, you would start with the temperature, the perturbation temperature, and then deduce what the various forcing functions have got to be. Of course, this equation is already explicitly written in terms of velocity components, so if you've actually got information about the velocity components, that sort of short-circuits it, and that's what we're doing here. I'm putting those in directly. Right, well, I suppose I better show you what the system looks like. So this is an exact evaluation of that solution that I showed you with the Bessel functions in. So I've plotted it. It is 0 at the very bottom because it's the no-slip boundary condition. So I've shown you what the mean zonal velocity looks like. 10% up from the bottom, so it's a scale of about 2.5, going up to 25 here when you're 90% up, and this is about 60% up. What I think, however, is, which is no surprise, because that's going to follow fairly closely the particular integral that I've introduced. What happens, though, to the meridional? Well, let me show you. These are in exactly the same, 10% up, 60% up, 90% up. Quite a few little things to notice here. So this will be 0, of course. The viscous boundary condition puts 0 at the very bottom. So a little bit up from the bottom, you've got an oscillatory structure. You'll notice this little kink here. I thought that's one of the reasons for choosing theta is minus 10 degrees. If theta was 0, theta naught was 0, that would just go straight through. There's no little hiccup there. In short, it doesn't make any fundamental difference to the formulation of the problem. Right, as I've shown it, at 60% up, you're beginning to see a switch from that polarity to that polarity. Remember, this is the meridional. So if we're going to have cells, okay, 3 cells, then we're going to have the polarity of the meridional changing sign. So this is the bottom, 1, 2, 3, the cells relatively near the bottom. These are the cells very near the top. Yes, before you ask, I did compute, I'm not going to show it to you because it's a bit messy, but I've also computed the W. That was rather more difficult to get hold of through this theory, but you can do it. But the amount of computing time was absolutely enormous, and that just confirms that we've got the 3 cells, the Hadley, the Ferrel, and the polar, via this representation, which is via, because of the special choices I've made, Bessel functions. Okay, let's go to something else. Have a look at the Walker circulation. So again, some of you will perhaps be familiar with this. So in a narrow band along the equatorial Pacific, we have the Walker circulation. The equations that we're dealing with, I'm just quoting them again, look like this. And we can look at these equations in a relatively general way. And I'll show you something even more powerful, I think, towards the end, using these sort of arguments. So remember what as I said at the beginning, I'm combining here some of my investigations and some of Adrian's investigations, and looking at this system of equations that we've developed. Okay, so we assume that the flow is inviscid at the very top of the troposphere, and we have a no-slip condition at the bottom. General considerations are all that we require. It follows that necessarily the zonal flow must reverse. It's westwards near the ground and eastwards near the top. We don't need to write down explicit solutions to get this information out. In particular, in a little bit more detail, there is a height in the troposphere above which U0 increases with height and below which U0 decreases with height. If you like, let me spell it out like this. If you look at the zonal speed, viewed from the bottom to the top, it starts at 0. That's our no-slip boundary condition. It becomes negative, it's westwards, but then it increases positively and eventually does indeed become positive eastwards. I would argue that this is one of the great advantages of using a reliable background set of equations. We know exactly what their validity is, we know where they've come from, we haven't had to make auxiliary assumptions or approximations to get to this stage. The only one we're making, having written down our model, Navier-Stokes, first law of thermodynamics, whatever, is the use of the thin shell approximation. Everything else is just carried through. Right, so that's worked out very well. So, concluding remarks. What I've tried to do then is to invoke the thin shell approximation and essentially nothing else. We naturally produce a background state and a perturbation to that background state, which seems to embody all the main linear dynamics. The nonlinear terms come in at the next order, by the way, and they are uniformly small. There are no non-uniformities in the velocity field. So the nonlinearity will always be small compared with the linear system. It doesn't seem that there can be any, there could be, of course, very, very special configurations in which case, for which the order epsilon term is very, very small, and you need the order epsilon squared term, but there may be experts in the room who can tell me that could happen. But on the face of it, no. We can obviously recover familiar results, and we've begun to hint at slightly more sophisticated results, Ferrel and Walker circulation. I claim that we can look at many other appropriate, large-scale motions of the atmosphere. And as I said way at the beginning, we're beginning to look now at the time dependence in this problem so we can incorporate waves. And my suggestion would be that the equations, the perturbation equations that we've got with suitable forcing and all the generality you want to put in will be ripe for numerical analysis. And there is just one thing more. Rather repeating, I'm trying to make the point that once we've got these equations, there are quite an amazing number of things we can do. Let me remind you of this governing function sigma 1, which is the fundamental driver. We can look at a flow problem at zeta fixed. So we look at a region where the flow is essentially inviscid, then necessarily the particle paths must sit on those level curves. That means that we can draw the phase portraits without having to solve the system of equations, so we can find the particle paths and examine critical points. Indeed, we can go one stage further using this structure. We can show that each jet stream is sitting at the separatrix, which is between the closed particle paths of this function around the maxima and the minima. So we've maxima, minima, and the jet streams sit between them. In short, I hope that this approach to the study is something different, something new, and I would like to suggest it opens up many avenues for further investigation. Shall I press it? Thank you. I think I'm supposed to use this for you to ask the question. Okay, it's just so it'll be recorded. You don't mind?
Okay. Is it possible that your cosine squared latitude terms originate from the fact that you neglected the ellipticity of Earth? In other words, had you done it in a slightly more accurate with respect to Earth, your theta dependence would have gone away?
No, I don't think so. The adjustment that I could make in that theory is not to put the bottom at z is equal to 0. I could put the bottom at z is equal to a slightly distorted function, but it won't alter the size of those cos theta terms. They're still going to be there. They aren't sufficient to remove, I'm sure. But I can check.
Okay.
Yep.
And one more remark, it's not the question. Your non-dimensional G, you quoted as 0.7 or so.
Yep.
I would argue it's about 2 orders of magnitude smaller than that because the speed of gravity waves in the troposphere is about 30 meters per second, and your scale was about 450. And you take that squared, which is about 3 over 450 squared, so it's like 1 in 200.
I think I checked those numbers pretty carefully. I will check them again.
No,
But,
I'm talking about the observation in terms of
Oh,
the
I'm sorry. Okay.
observed gravity waves in the troposphere
Yes.
are about order 30 meters per second, while I think
Well, that could mean, I mean, we haven't yet looked at time dependence. That could well mean that when we look carefully at the time-dependent problem, there are additional scalings that are going to be needed, which can change the size of the parameter that's needed in a particular configuration. That's an open question.
well, it's
And
going to
you may
knock
be
down
right.
your G by 2 orders of magnitude.
Sorry?
I'm saying it's going to knock down your G by about 2 orders of magnitude. I'm not quite sure how it will change your results.
Yes, but that's not going to be relevant here, you're saying, because we haven't got any waves here. Well,
Possibly, yeah.
yeah. Okay. Yes.
So a related question to that, I quickly scribbled down your velocity scale that you assume d times h, and it comes out to less than 1 meter per second.
Yep.
And typical horizontal velocities aren't that small. In maybe the residual circulation in the atmosphere, but not the actual main jets that
But,
are 30, 40 meters.
this is U naught, V naught, whatever, can be any numbers you like. It's just their parameter dependence in epsilon.
Right, but when you put in a scaling, when you go through the scaling, then I think, as Nathan pointed out, there can be other small parameters that may be arising in your problem, or large parameters that
But where
you
from?
assume to be order
I
one.
mean, there aren't any other physical elements within the equations to give you any other parameters. The parameters there are the full set of independent parameters for that particular system of Navier-Stokes, first law, etc. There aren't any other free parameters around.
Okay. One tiny point was that at the end you talked about an inviscid problem where you have sigma 1 as an inviscid invariant.
Yeah.
We know that in the problem, the full problem, there should be conservation of potential vorticity and potential temperature.
Right.
So is there a second one?
I can't answer. I just don't know. Okay. But I certainly need to, there are, as you realise, this is still ongoing, very much ongoing. And what we were hoping would happen in this context is that indeed some of the issues that are beginning to be raised are things that we need to address. It is obvious that my background is in classical fluid mechanics and asymptotic expansions. It's not in the atmosphere, and I'm learning all the time, and I wish to continue learning. Thank you.